So today we're going to have a look at the countercurrent mechanism of the kidney. Now, first of all, when we're looking at a nephron, the descending limb, the loop of Henle has two limbs. We can see that this one is the descending limb, this is the ascending limb, and they're both thin. So the descending limb, this part here of the loop of Henle, is permeable to water but not to solutes. So it helps to allow water to exit into the interstitium. And the ascending, so the TAL, the thin ascending limb of the loop of Henle, is impermeable to water, but it helps the transportation of a couple of different solutes like sodium, potassium, and 2-chlorine. So this uses a specific channel called the sodium potassium chlorine co-transporter. Now, they actively transport sodium and chloride ions into the interstitium, so this helps to create a hyperosmotic environment. Hyperosmotic means that you have an increase in osmolarity. Now, we have a specific thing right here. It's a blood vessel called the vasorector. So the loop of Henle is your countercurrent. So countercurrent means that it's not straight. It's got this sort of loop. Countercurrent exchanger, and you also have a countercurrent. So this one will be your exchanger, and this one will be your multiplier. Multiplier and exchanger. So you can see both the vasorector and the loop of Henle have this sort of loop here, right? And when we're looking at the vasorector, it's just capillaries that run parallel to the loop of Henle, and they help to maintain that osmotic gradient, which is established by this loop, and it prevents to wash out different liquids. So let's say that if this is the vasorector, we start off with 300 milliosmoles per liter. It goes down and becomes more hyperosmolar up to here where it's this. If it continued down straight, we would lose a lot of solute, because here it's reabsorbing solutes and it's getting rid of water, so we're getting more concentrated. But as we move up the loop, it starts to get rid of those specific solutes like sodium and chlorine and potassium, all that. So it starts to get rid of those, and at the end you end up with 325 milliosmoles. So you're not gaining much, and it's a very slow sort of blood flow, slow and steady. We also have urea recycling that happens right here. So in the later part of the medullary collecting ducts, and urea is reabsorbed from the inner medullary collecting ducts into the interstitium. So right at the end, this is where some of the urea is reabsorbed, especially if you have a high protein diet, and because of protein synthesis, there's so much urea that's left over. So it's going to go through these nephrons, and around 50% of the urea is going to get reabsorbed in the proximal convoluted tubule. The rest of it's going to move down, and at the end of the collecting duct, we have some, it's basically permeable to urea reabsorption, but majority of it does go down into urine. And let's say that if some of the urea is reabsorbed, then what can happen is it can be secreted into the thin ascending limb, and this recycling contributes to the high osmolarity of the medulla, and it can also help with water reabsorption as well. So let's say if it's reabsorbed, it can go back into the thin ascending limb and then go back into this loop, and it can keep going and going until some of it gets reabsorbed, some of it gets reabsorbed and some of it goes down into urine. Now the last thing I want to talk about is ADH, or antidiuretic hormone. So if we have a look from the very beginning, what happens is in the brain you have these osmoreceptors and angiotensin 2. So you would know the process of angiotensinogen from the liver getting converted into angiotensin 1 from something called renin, which is secreted from the juxtaglomerular apparatus. And from that, what happens is you get angiotensin 2 using an enzyme called ACE, so angiotensin converting enzyme. So let's say we got that, right? We got angiotensin 2, it goes into these receptors, binds to it, and we have a supraoptic nucleus, blah blah blah. Don't really need to know much of that. You just need to know that from the posterior pituitary, you have antidiuretic hormone that gets secreted, and it binds onto these V2 receptors on the principal cells of the collecting duct or the distal convoluted tubule. What happens, it goes through some sort of like all of those cascades, makes adenylate cyclase, which helps to make CAMP, protein kinase C, which can help to stimulate the production of aquaporin 2. And this helps to absorb water into the principal cells. And then these water channels help to move water, and some of it can go into the interstitium using the aquaporin 1 channels, and this can help to increase the blood pressure and decrease plasma osmolarity because you have more water in your blood. So that's basically what happens. But if we have a look at the bigger picture, you can see CAMP, protein kinase C. So these aquaporin channels, the second ones, these ones are only created by ADH, and they help to bind onto the basolateral membrane. And once they do that, they help to increase water reabsorption. So this 60 milliosmoles is going to get reabsorbed, and this hyperosmolar interstitium is going to become more diluted. So if all the water is going out, what's going to happen to the urine that's left? It's going to become concentrated, and therefore you get concentrated urine. Now, this is because of the presence of ADH. Let's say if ADH wasn't there, you wouldn't have these aquaporin 2 channels, which only form because of ADH. Here we have aquaporin 3 and 4. They're always there, so they are not hormone dependent, as compared to aquaporin 2 channels, which are hormone dependent, so they're dependent on ADH. And because if you don't have ADH, you won't make these, they won't go into the basolateral membrane, and you won't help to make water move out. So the hyperosmolar interstitium is going to stay hyperosmolar, and that's going to cause this to become more diluted because the water hasn't gone out, and so you get diluted urine. So that's how you can see that ADH plays a big role in the concentration or dilution of urine.